Hey everyone. So, have you ever stopped to think about how a machine learning model makes sense of our world? How it can possibly compare something like a person's age, say 40, to their salary, which could be, hundreds of thousands of dollars. To an algorithm, those numbers are just worlds apart. Well, today we're diving into the really elegant technique that fixes this, leveling the playing field for all your data. We're talking about normalization.
Here's what we've got on tap. We're going to start with the why, the problem that different scales create in the first place. Then we'll get into what normalization actually is, and, of course, how it works with a super simple example. After that, we'll get practical and cover when you should use it, and, just as importantly, when you shouldn't. And we'll wrap it all up with the key takeaways.
All right, first things first, let's get right to the heart of the issue, the problem of scale. And this is a really sneaky one, because without you even realizing it, the way your data is structured can totally bias your model's results before you've even started training.
To really get this, let me ask you a question. If you have a data set with both age and income, which one do you think an algorithm would see as more important? Now, you and I know that both of these can be super relevant, but an algorithm, well, it doesn't have our intuition. It just sees the numbers.
And this is where it gets crazy. Look at these numbers. The range for age is just 40, but the range for income, it's almost 2 million. For any algorithm that works by calculating distances, think K-Means clustering or K-nearest neighbors, the huge numbers in the income column are going to completely overwhelm the tiny numbers in the age column. The model will literally think income is thousands of times more important just because the numbers are bigger. The influence of age just gets totally drowned out.
So, how in the world do we fix this huge imbalance? Well, this is where our hero, normalization, steps onto the scene. It's the technique that's designed specifically to bring that balance and fairness back to your data. Okay, so the textbook definition is that normalization is the process of rescaling your numbers into a fixed range, and that range is almost always between 0 and 1. Now, here's the really crucial part. It does all of this without changing the basic shape or distribution of your data. It just kind of squishes everything into a smaller, common space.
A really great way to think about it is like a universal translator. It takes all these different features measured in dollars, years, centimeters, whatever, and it translates them all into the same exact language, a simple, common scale from 0 to 1.
And why do we care so much about this translation? Well, it's absolutely critical. It makes sure every feature gets an equal say, which directly boosts your model's performance and training speed. Plus, it's basically a non-negotiable for things like neural networks, where these wildly different scales can cause the calculations to just explode and make the whole learning process unstable.
Okay, so we know what it is, we know why it's important, but how does it actually work? Let's peel back the curtain and look at the most common and, honestly, the most intuitive method out there, called min-max scaling.
Now, here's the formula. And don't let it scare you. I promise it's way simpler than it looks. All it's really doing is taking your value, subtracting the smallest value in that entire column, and then dividing that by the total range of the column. It's basically just figuring out where does my number fall on the spectrum from the absolute minimum to the absolute maximum.
Let's make this real. Imagine we have a salary of $50,000, and in our data set, the lowest salary is $20K and the highest is $80K. Step 1, we see how far our value is from the bottom. That's $30,000. Step 2, we figure out the total range of all salaries, which is $60,000. And finally, step 3, we just divide the two. $30,000 divided by $60,000 is 0.5. And there you go. The normalized value is 0.5, placing it smack dab in the middle of our new 0 to 1 scale. Simple as that.
So this is a super powerful tool, right? But you wouldn't use a sledgehammer to hang a picture frame. So let's talk about the practical rules of engagement. When should you actually be using normalization, and when is it okay to just skip it?
Okay, so when is normalization an absolute must-do? Well, it's essential for any of those distance-based algorithms we talked about, like K-nearest neighbors or K-means. It's also a must for neural networks if you want them to train efficiently and stably. And here's a great rule of thumb. If your features are measured in different units, like height in centimeters and salary in dollars, normalize them. Same goes for image processing, where you'll almost always scale those pixel values from 0 to 255 down to that clean 0 to 1 range. And when can you just not worry about it? Generally, you're safe with tree-based models like decision trees, random forests, or XGBoost. They just care about split points, not the actual scale of the data. And of course, if your features already happen to be on a similar scale, then you're good to go. But
Here's a really important warning. If your data has some extreme outliers, min-max scaling can totally backfire. In that case, you'll want to look at other techniques.
And that brings us to a super common point of confusion: normalization versus standardization. This table really breaks down the key differences. The big thing to remember is that normalization squishes your data into a fixed 0 to 1 range and is really sensitive to outliers. Standardization, on the other hand, it rescales your data so it has a mean of 0 and a standard deviation of 1. It doesn't have a fixed range, but it's much less bothered by outliers. So the choice really comes down to your data. If it's pretty clean and you need that strict 0 to 1 range, go with normalization. But if you're worried about outliers, standardization is probably the safer bet.
All right, let's bring it all home. We're going to wrap this up by summarizing the most important things you need to remember about normalization.
So, what's the big advantage here? At the end of the day, normalization is all about fairness. By leveling that playing field, you're letting your model learn faster and more reliably. You're making sure that the patterns it finds are real, and not just some weird side effect of using different measurement scales.
But, it's not a silver bullet. Its biggest weakness, by far, is its sensitivity to outliers. A single crazy value can squash all your other data points into a tiny little corner of that 0 to 1 range, basically hiding all their useful information. You also lose the original units, which can make things harder to interpret, and this is a big one. You have to save the minimum and maximum values from your training data so you can apply the exact same scaling to any new data you get later.
And here's a fantastic little reference slide to keep in your back pocket. We've mostly talked about min-max, but that's really just one tool in a much bigger toolkit. You can see there are other methods out there like z-score, which is that standardization we just talked about, and others that are designed for really specific tasks like text analysis. The important thing is just to know you have options and you can pick the right tool for your data and your goal.
Normalization isn't just some technical step you have to check off a list. It's about letting every single feature in your data tell its story fairly. It's about unlocking the real patterns that are hiding just beneath the surface. So the question I'll leave you with is this. Now that you've leveled the playing field, what will your data reveal? Thanks for tuning in.